All right, welcome everyone to my 11.6 video. I'm starting off here on our D2L page just for a few administrative announcements, and then we'll get into the math. So the first thing that I thought I'd just bring up, we have now nicely over here on the right-hand side some web work due dates. I think we're going to try to keep up with those, although I'm noticing that they say 11:59 a.m. That probably should be p.m., so those probably need to be edited. But yeah, we're going to try to keep up to date with some web work due dates over here on the right-hand side. The other thing that you see is the upcoming lab, right? So usually on Friday's class, I would make some announcement about the next Tuesday's recitation. So next Tuesday's recitation is a lab. Those are changing, as you probably recall from this very long bit right here about how labs and all that sort of stuff are changing. So those are going to be individual responses. I think we're going to be loading it onto D2L. There was a little bit of back and forth between D2L or a Google form, but I think we're going with D2L, although that may change between now and then. So you'll get an announcement as soon as that's ready and created and all that sort of stuff. But yeah, so next week is going to be a lab, and those are going to be a little bit more individualized, but you're allowed to collaborate, so you're allowed to use Piazza and all that sort of stuff. So, all right, that's my, I guess, administrative announcement for this video. Now let's go ahead and transition and start to talk about some math. So, 11.6, again, this video is assuming that you watched the two videos, the kind of standard videos before this as part of the class notes for 11.6. So if you haven't done that, you should pause this video, you should go watch those videos and then come back, because I'm assuming that you know the definitions, the theorems, and you've seen a few examples and have those under your belt already. But okay, assuming that that's the case, let's move forward. 11.6 here, as promised, right? I kind of in my 11.5 class videos, I brought up these definitions for absolutely convergent and conditionally convergent. And so you see those, like I promised, formally brought up here in 11.6 as well. And then we get into, so okay, here's this theorem that I also, at the time I told you it was a bonus theorem, right? If you have an absolutely convergent series, then it is convergent. So you don't have to worry about the original series or anything like this. Great. And here you get into the meat of this section, and that is the ratio test. And let me tell you, this is really everybody's favorite test. And let me tell you why, right? So the ratio test, it really doesn't have anything for hypotheses, right? So like the integral test, there's a lot of hypotheses that you had to check. Even with the alternating series test, there's a couple hypotheses that you have to check. So this really doesn't have so much in line as hypotheses, so it's not quite as annoying. The other thing, like with the limit comparison test or the direct comparison test or things like this, right, you have to make some choice. You have to go out and find something to compare with. For this one right here, you don't have any choices to make, right? It's just take the ratio of these subsequent terms in the sequence, figure out what their limit is, and if it's less than 1, then we get absolute convergence. If it's greater than 1, then we get divergence. But sadly, as we see here, the ratio test does not solve every single type of problem. It does have the possibility that sometimes it's inconclusive. Sometimes it doesn't know if the series is going to converge or if the series is going to diverge. And in which case, right, you need to go out and you need to use a different test. So the ratio test does not take care of all problems. Very similar to chapter 7, right? There is no one technique of integration that solves every single type of integral problem, right? Sometimes you have to use different tests depending on what the series looks like, or what the integral looks like back from chapter 7. So that's kind of the big thing here for this section, the ratio test. And in today's class videos, we're going to do more examples related to the ratio test. And that's what we did for the rest of the video here. So those are the videos that you should have watched in a nutshell. Let's go ahead then and move on to our problems for today. So here, I'd like to go over these problems related to the ratio test. So here's the question for the first problem. Are the following series absolutely convergent, conditionally convergent, or divergent? And so here's what I have. This series starting at n equals 1, going to infinity, negative 1 to the n, divided by n factorial. So this is kind of a nice quick problem, but let's do actually some quick review, right? Just in case if you've forgotten what these factorials are. So let me show you kind of a nice review. So 5 factorial, just as a reminder here, with a little exclamation point here, means 5 times 4 times 3 times 2 times 1. And right, you really don't even have to include the times 1 if you don't want to, but it's multiplying the first 5 integers together, 1, 2, 3, 4, 5, or the first 5 positive integers together. And so if you multiply all of these things together, you should get 120. So 5 factorial is 120. And so in general, if you have n factorial, this would be n times n minus 1 times n minus 2 times all the way down to 3, then 2, then 1. So that is what n factorial means. All right, and with this, let's go ahead and try to solve this problem here. Of course, we're in the ratio test section, and so we're maybe apt to try the ratio test. And again, like this is a pretty nice test, so let's go ahead and give it a go. Remember, the ratio test is looking at the limit as n goes to infinity. And we're going to take the n plus first term, divide it by the nth term, take the absolute value of that, and again, we're going to let n go to infinity. So let's go ahead and use our specific series here. We're going to get the n plus first term. So remember, this is just the nth term right here. So everywhere I see an n, I'm going to go ahead and write an n plus 1. So I'm going to have negative 1 raised to the n plus first term divided by n plus 1 factorial, and then I'm going to divide that by the nth term. So that's going to be negative 1 raised to the n divided by n factorial, all inside of our absolute values. Now, quite often, you know, similar to when we were using the limit comparison test, we have all of these fractions and fractions divided by fractions and all that sort of stuff. So usually my first step is I'm going to go ahead and I'm going to multiply by the reciprocal here. So when I multiply by the reciprocal, negative 1 raised to the n plus first power, n plus 1 factorial, multiply by the reciprocal, n factorial divided by negative 1 to the n, and that just kind of cleans things up a little bit. All right, so we can see you actually are going to get quite a bit of cancellation, right? So in the top here, let me go ahead and change my pen color, we have n plus 1 negative 1s. And down here we have n negative 1s, right? So let's, assume that n is some, number like 5 or something like this, right? So we have 6 of these things on top. We have 5 of them on bottom, right? They're pretty much all going to cancel out except for you have one more on top. And so this we can go ahead and write, right? There's a lot of cancellation, except for you're just going to have one more on top than you do on bottom. And so I'm going to say the limit as n goes to infinity of negative 1, right? You have one more on top than you do on bottom. And then here we have n factorial divided by n plus 1 factorial. All right, now with these absolute values, right? The absolute value of negative 1 is just going to be 1. That's quite nice. And then these factorials, right, they're just products of positive numbers, right? So all of these are positive integers that we're multiplying together. And so the absolute value is not going to do anything for this. So I'm going to write the limit as n goes to infinity, and the absolute value of negative 1 is 1, and the absolute value of a bunch of positive things is just positive. All right, so now we need to know, how do these factorials cancel, right? How do these factorials cancel? Well, maybe for this one, I'm going to give you a nice theorem here, and in fact, you've already probably seen it, but I'm just going to reiterate here. I'm going to give you a nice theorem. However, let's write this out and really show what this is. So limit as n goes to infinity, n factorial quite literally means n times n minus 1 times all the way down to 3 times 2 times 1. So that's what n factorial means, and again, that's just using this up here. N plus 1 factorial, that just means you start one higher. You start off at n plus 1, and then the number below that, that's going to be n, and then the number below that, that's going to be n minus 1, and again, you go all the way down to 3, 2, 1. And you can see here that there's an extreme amount of canceling that happens, right? N cancels with n minus 1 cancels with n minus 1, all the way down to 3 cancels with 3, 2 cancels with 2, and the ones, I guess they cancel with each other, right? And so we're left here, everything cancels except for there's an n plus 1 in the bottom. And so the theorem that I would like to give you, and that you've probably already seen, is that n plus 1 factorial is the same thing as n plus 1 times n factorial. So basically, we're just grouping together the multiplication of the first n items here, and then we're including this n plus 1 here, and that altogether would be n plus 1 factorial. So with this, you can kind of quickly see, right, if I was to rewrite this, let me just bring this off over here. Instead of having to use that definition, if we just use this theorem, we could say n factorial divided by, and I'm going to say n plus 1 times n factorial, and now we can just see that those n factorials cancel. So you can do this if you happen to remember this theorem. It's wonderful. If you don't happen to remember this theorem, that's fine. Just remember the definition, right? The definition gives this to us. It takes an extra step, but you don't have to memorize anything more. So now as n goes to infinity, this is going to be equal to 0. Again, our numerator is constant. The denominator is growing off to infinity, and this is certainly less than 1. Remember, you have to be very careful, right? For the limit comparison test, 0 was a bad answer. For the limit comparison test, right, we wanted something bigger than 0, less than infinity. But for the ratio test, right, 1 is a bad answer. 1 means it's inconclusive. It didn't work, right? And so you have to be careful, right? With the ratio test, this is a good result. With the ratio test, we can say, by the ratio test, since we got an answer less than 1, we know that the series from n equals 1 to infinity, right, the series we were given here, negative 1 to the n divided by n factorial, that this converges, and better yet, the ratio test says that it converges absolutely. So I'm going to say that it converges absolutely. And again, that's what we're trying to figure out, right? Does it converge absolutely, or is it absolutely convergent? Is it conditionally convergent? Is it divergent? What's going on here? And so the ratio test says that this is absolutely convergent. All right, with that, why don't we go ahead and try one more here, kind of a similar strength or similar difficulty. I recommend that you pause the video, try this one on your own, and then let's go over the results together. So again, please pause the video, try this one, see how far you can get, then resume watching. All right, so here is my result. Again, we take the limit as n goes to infinity, the absolute value, and we do a sub n plus 1. So everywhere I see an n up here, I plugged in n plus 1. That gave me my first bit. And now notice that I've skipped a step, right? Eventually you're going to get to doing so many of these, right, that you're just going to start multiplying by the reciprocal automatically, right? And it's fine that, if you're not there yet, but this is okay work to show, for quizzes and exams and all that sort of stuff. So I've just multiplied by the reciprocal. So I have the reciprocal of negative 1 to the n here. I have the reciprocal of 5 to the n divided by n there. And so, okay, we can see that there's a bit of canceling that happens. So notice that we have one more of these negative 1s on top than we do on bottom, right? Whatever 1 is, there's n plus 1 of them on top, and there's n of them on bottom. So a lot of canceling happens, and you're just left with 1 left over on the top. And a very similar story for the 5s, right? You have n plus 1 of them on top, and you have n of them on bottom. So there's a lot of canceling that happens, and you're just left with 5 on top, right? You're left with 1 more on top. N of them cancel here, n of them cancel here, so you're left with 5 on top. That's this bit. And then these ones don't cancel as nice. We have an n, and we have an n plus 1. So I'm just going to leave those for the time being. When I apply my absolute value, so that's my next step, jumping to the third line here, the absolute value of negative 1 is 1. The absolute value of 5 is 5. And remember, n is going off to infinity, so it's certainly positive. And so when you take the ratio of positive numbers, it stays positive. And so the absolute value just can kind of go away, right? Once we've gotten rid of this negative 1. Now, as n goes to infinity, notice this 5 is just a constant. It's along for the ride here. And then we have n divided by n plus 1. And there's a variety of ways to say that that is going to be going to 1. So there's the algebra way, right, which says that these are polynomials of the same degree in the numerator and the denominator. And so the limit should be this ratio of leading coefficients. Or you could use the Calc 1 way, in which case you would divide by the highest power in the denominator. That's n to the first power, and that would give it to you. Or you could use L'Hopital's rule. So any of these would work. In all cases, you get 5, right? 5 is greater than 1. Remember, with the ratio test, we're always comparing against 1. If it's less than 1, it converges absolutely. If it's greater than 1, it diverges. And so the case here, we can say, so by the ratio test, we know that our series, summing up from n equals 1 to infinity, -1 to the n, 5 to the n, divided by n, that this diverges. There we go. And again, we were trying to classify it, right? Does it absolutely converge? Does it conditionally converge? Or does it diverge? And we've found that it diverges. All right. Let's go ahead and move on, and I have another one here for us. This one's also not so bad, but let's work through this one together. All right. If you'd like to, I guess, you can always pause the video and try it on your own. That's certainly allowed. But let's go ahead. The limit as n goes to infinity, we're going to try to apply the ratio test here. We're going to have the absolute value, and again, I'm plugging in n plus 1 everywhere I see an n. So -2 raised to the n plus 1. I'm going to go ahead and multiply by the reciprocal here. So -2 to the n and n squared. So again, normally this is the ratio a sub n plus 1, the nth plus 1 term, and a sub n, the nth term. Now let's go ahead. And for all of these, you can see kind of what I've been doing is that I've been grouping together these like pieces. So even though I haven't formally rearranged these things before, really I'm kind of bringing all of these polynomials together, and we need to think about these. And I'm bringing all of these exponents together, and we need to think about these. And so in this case, we can see that we have one more -2 on bottom than we do on top. And so when these things cancel, all of them cancel on top, and we have one -2 left on bottom. Let's go ahead and apply these absolute value signs now. So the absolute value, well, we have a bunch of things squared, so that's already positive. We really don't need any more positive, I suppose, over here. It's already positive. And then when we go ahead, let's see, I guess we would have a 1 on top, and we need to take the absolute value of that -2 that's hanging out there in the bottom. So the absolute value of -2 is going to be +2. And now we have to figure out, okay, how am I going to evaluate out this limit? Again, this is one of these indeterminate forms. It's an infinity over infinity indeterminate form. We could certainly use L'Hopital's rule for this. We can use our Calc 1 strategies, or we can use algebra, right? Because it's polynomials over polynomials. And so in all cases, what we're going to end up with is that this is just 1 times 1/2. So right, the limit as this bit right here goes to infinity. Again, if you wanted to use L'Hopital's rule, that would be a fine way to go. Those 2's are going to come down and take L'Hopital's rule one more time. Again, this is going to be going to 1. Or probably my favorite way is I usually like using algebra. Let me go ahead and just show you what I would do here for the algebra. Right, this would be n squared plus 2n plus 1 if we were to FOIL out the top. N squared on bottom. And again, we have polynomials of equal degree in the numerator and the denominator. And so the answer is going to be, right, the horizontal asymptote, or the limit as n goes to infinity, is just going to be the ratio of these leading coefficients. So 1 divided by 1. So that's another way that you could show it. There are several others, right? So, okay. This is, again, all roads lead to this answer of 1/2. Oh, sorry. The answer is 1/2. I was trying to do two things at once. 1/2 is not less than 1/2, actually. 1/2 is less than 1. That's certainly a fine thing to write. But yeah, so this is 1/2. It's less than 1. And remember, with the ratio test, we're always comparing against 1. So I can say here, by the ratio test, we know that our series, summing up n squared divided by -2 to the n, will converge absolutely. Converge absolutely. So that right there would be my final answer. So again, you're always going to do a bunch of work, and then you're going to have a conclusion statement. So in this case, by the ratio test, that's why it converges absolutely. Okay, let's go ahead and try this one here. And this one has a bit of a surprise to it. So I would like you to go ahead and pause the video for this one and try it out on your own. Get as far as you possibly can, and then we're going to work on it together. So again, please pause the video and be prepared for a bit of a surprise. All right, good luck. All right, so here is the work that I came up with. As you can see, this problem is a bit more difficult. So what I've done here is that I have my a sub n plus 1. I've divided by my a sub n, and again, I've went ahead and I've just multiplied by the reciprocal. And then I've gone ahead and grouped like terms. So my next step here is that I've grouped like terms all of the natural log bits together and all of the cube bits together, right? Notice that I took away the absolute value. This is a bit of a silly question, right? Because this is not an alternating series. And so it doesn't really have the possibility of really being conditionally convergent. It's either going to converge, in which case, again, these absolute values really didn't do anything. There wasn't an alternating piece, or it's going to diverge. So in the case where you're asked this sort of question, that's fine. I mean, technically you can ask this question. However, there's not really the possibility for it being conditionally convergent because it's not an alternating series. Okay, so we got rid of the absolute values because, again, everything's positive. Starting at n equals 1 and beyond, the natural log is positive, and certainly n and n plus 1 is positive. All right. So the absolute value is gone. Notice I also did this trick where I took everything, right, all of the cubes, and I put them inside of one cube, right? So we had n cubed on top and we had n plus 1 cubed on bottom. This ends up being really nice because, remember, limits can be pushed inside of continuous functions. And so instead of trying to figure out what the limit of this entire thing is, if we can just figure out what the limit of the inside bit here is, in this case we can quickly say that it's 1, then we can just cube that answer. In this case, 1 cubed is just 1, and that's our final result. So this is kind of a bit of a shortcut. Otherwise, you would have to use some L'Hopital's rule. You'd have to expand things out, but this is perfectly acceptable work. Okay, on the other hand, the natural logs don't work out so nicely, right? There's nothing, you can't group together and just make this one natural log. Sadly, that's not a valid property of the natural logs. And so, instead, we can apply L'Hopital's rule, right? If you were to, plug in infinity, essentially everywhere you see an n, this would be an infinity over infinity indeterminate form, so you're allowed to use L'Hopital's rule. And so for my next step here, I took the derivative of the natural log, that's going to be 1 over, and don't forget about the chain rule, right? So that's where that extra multiplication by a 5 comes in. And likewise for the denominator, right? The natural log of 5n, when I take its derivative, I get 1 over 5n times chain rule, don't forget that, right? The derivative of the inside, 5. So, of course, we can see that there's a bit of canceling that happens. These 5s go away. That's fine. And instead of dividing by a fraction, this 1 over 5n, we could multiply by its reciprocal. So we get 5n divided by 5n plus 5. Now, as n goes to infinity, again, this is much simpler now. We can go ahead and take those ratios of the leading coefficients here, since these are polynomials of equal degree. So 5 divided by 5, this is equal to 1. And this was the surprise that I was hoping for, I guess, expecting here, is that when it's equal to 1, remember the ratio test is inconclusive. So the ratio test is inconclusive. And that deserves a frowny face, certainly. And so the question is, well, if the ratio test doesn't work here, what should we do, right? Because again, this doesn't say, this example isn't all about the ratio test. The example is, hey, here's a series. Tell me if it converges, if it's conditionally convergent, or maybe if it diverges, right? And so we need to figure out, maybe we try the ratio test, right? Imagine that this was a quiz or an exam question or something like that, right? It doesn't work. Where do we go next? Well, let's go through kind of our checklist here. Back in 11.2, we had something called the geometric series test. Will the geometric series test work on this? Well, no, sadly, because it's not a geometric series, right? We would need an a times r to the n, where a and r are all constants. What about the alternating series test, right? So that was something that we got in 11.5. Well, we already talked about, so sadly, it's not an alternating series. So that's kind of out. If you tried the nth term test for divergence, that's a good thing to try, but sadly the limit would go to 0. And so when the limit goes to 0, remember that tells you nothing, right? It's inconclusive. It doesn't know if it converges or if it diverges or what's going on. P-series only works when you have 1 over n to some power, but this natural log kind of ruins that for us. So sadly, p-series is out as well. Integral test, well, you could sit and you'd have to spend a little bit of time to try the integral test. And I would claim that this is very hard to integrate, and so I would not recommend using the integral test. Usually I save the integral test for last anyway. So we're on to the comparison tests, right? I would usually think about the limit comparison test or the direct comparison test before the integral test. And remember, I told you guys for the limit comparison test, that usually has some problems with natural logs and sometimes these trig functions, right? Sine and cosine. And so it turns out the limit comparison test, there's no good way to do it. And so we're left with the direct comparison test. And the direct comparison test will indeed be the answer. And so let's go ahead and talk about this together. How can we use the direct comparison test in order to come up with this result? We need to remember, I told my class, right, it's a very nice comparison that we can make with the natural log. And technically this is only valid when n is 3 or bigger, right? But sine and cosine kind of have these very natural comparisons. But the natural log also has some nice comparisons. The natural log is going to be greater than 1, so long as what you're inputting is 3 or bigger. And then the next thing is that the natural log is always less than the square root function, so less than root u. And so this is some natural stuff that we can compare against for the direct comparison test. Now remember, for the direct comparison test, I don't always know which one of these inequalities that I necessarily want. And so I kind of hedge my bets to some extent, right? I set up both inequalities whenever possible, and then I have to think about it later, right? Which one ends up being useful? Okay, so remember that I have the natural log of 5n, and I'm going to divide by n cubed. So maybe on my right-hand side here, I'm going to want the square root of 5n, and I'm going to divide by n cubed. And then on the other side, I'm going to want 1, and again, I'm going to divide by n cubed. So these are the inequalities that maybe I would set up. Now, of course, I'm most interested in over here. Over here, I could tell you, right, if we were to sum up 1 over n cubed, I know very, very quickly that this converges. So this is going to converge because of p-series. Now, if you have a smaller function converging, does that tell you anything about a larger function? Does that keep it from going to infinity, for instance? And sadly, the answer is no, right? Just because a smaller function converges, that doesn't guarantee that a bigger function doesn't diverge. And so sadly, this one's out. And that's again why I've hedged my bets, why I've brought up kind of both of these inequalities, and then I'm going to figure out maybe which one's useful. So on the right-hand side, we have to do a little bit of work. I would go ahead and maybe rewrite this. Let's see, we have all this stuff inside of a square root. So this is going to be square root of 5 and square root of n. And then we could go ahead and do one more rewrite. Remember, square root of n, that's the same thing as n to the 1/2 power. So this is going to be root 5 and n to the 1/2 power divided by n cubed. That's going to be the same thing as n to the 2.5, or I suppose 5/2 power, right? So they cancel a little bit. The n's on top and the n's on bottom, they cancel a little bit, and we're left with n to the 5/2 on bottom. And now we can see, I guess if you really wanted to, you could do one more rewrite. I don't think this is so necessary. But this is also a p-series, right? So in this case, we have 1 over n to the 5/2. P is 5/2. That's greater than 1. And so this also converges, right? If we were to sum all of these up, this would also converge. And now if you have a bigger function going to some finite value, when you sum all these things up, right? A big series converging, does that guarantee that a smaller one will converge? Well, absolutely, right? There's no way that this one's going to go off to infinity, and yet a bigger one goes to something like 13, right? No, if a bigger one converges, the smaller one must also converge. And so we kind of have the right setup here for a direct comparison test. And so let's go ahead and write our conclusion statement. So since summing up from n equals 1 to infinity of root 5, 1 over n to the 5/2 converges by p-series, that tells us that our smaller series must also converge. So summing up from n equals 1 to infinity of the natural log of 5n divided by n cubed also converges thanks to the work of the direct comparison test. And again, we were asked, does something absolutely converge, conditionally converge, or diverge, right? And so in this case, remember that adding those absolute values doesn't do anything because these are already positive functions. And so in this case, the answer is that it absolutely converges. So converges, I'm going to say absolutely by the direct comparison test. So here would be my final answer, that my series converges absolutely. Why does it converge absolutely? Well, because of the direct comparison test. All right. Yes, that's that problem done. Again, I invite you, this is a fairly complicated problem, I admit that. And whenever you see a fairly complicated problem, right, it's fine to rewatch it several times. And if you still have questions and whatnot, again, I really want to encourage you guys to post them on Piazza or go to office hours, right? All of your instructors are going to be holding office hours, the TA's office hours. Go to the MLC, right? Continue to get help and really learn this stuff. All right. Moving on, though. Are the following series absolutely convergent, conditionally convergent, or divergent? Again, same sort of game that we're playing here, now with a different series. In this case, I've given you the written out version, right? So here's what the series actually looks like if you were to write it out. And then I've also mentioned what the pattern is, right? So where does that 1, 2, 3, 4 come from? Well, that's, of course, the n on top. Where does the 4, 7, 12, 19? Well, those are 3 more than perfect squares, right? And we can see that it's alternating. So that's that bit there. So why don't we go ahead and try, again, the ratio test, right? So for the ratio test, we're going to take the limit as n goes to infinity, the absolute value of, and now let's go ahead, -1 to the n minus 1 plus 1, right? We would add 1 to all of our n. So I guess let's just go ahead and write -1 to the nth power there, n plus 1 there, and n plus 1 quantity squared plus 3. So again, a sub n plus 1. Everywhere we see an n, we're writing n plus 1. Next up, we need to divide by our a sub n, and I'm just going to multiply by the reciprocal. So the reciprocal here, well, we'd have n squared plus 3 on top. We'd have -1 to the n minus 1 on bottom, and we'd also have n on bottom. Now let's go ahead and rearrange and maybe group together all of these like pieces. So I have -1 to the n, and I have -1 to the n minus 1 on bottom. I have n plus 1 on top, n on bottom, and I have n squared plus 3 on top. And let's go ahead and maybe FOIL this out and whatnot. What I'd have n squared plus 2n plus 1 on bottom. Oh, plus there's an extra 3 there. So maybe we could go ahead and just combine those, the 3 and the 1. That's going to make 4. Okay. So we have something that looks like this. Again, it's all inside of our absolute values. Let's maybe start simplifying things a little bit and see what those absolute values actually influence. And so looking at this first bit here, we can see that we have 1 more -1 on top than we do on bottom, right? N of them on top and 1 fewer, n minus 1 on bottom. But still, when we go ahead and we apply these absolute values, this is just going to be 1, right? Because the absolute value of -1 or 1 is just 1. The absolute value of n plus 1 is just n plus 1. The absolute value of n is just n, right? All of these things are positive values. We're plugging in n equals 1 and bigger. And so those absolute values aren't doing a whole lot after we take care of that -1 business. Now let's go ahead and think about the limit as n goes to infinity. So as n goes to infinity, of course, 1 is just 1. That's fine. N plus 1 over n, well, that's going to go to 1 over 1, or just 1. And n squared plus 3 over n squared plus 2n plus 4. Again, the leading coefficients here, we have polynomials of equal degree. And so it's just going to be the ratio of the leading coefficients. 1 over 1 is, again, 1. So multiply a bunch of 1s together, and sadly, again, we've gotten 1. And so the ratio test does not work. In fact, in 11.7, we're going to spend a little bit of time. We'll have a lesson about 11.7 here coming up next. And we're going to talk about what are some key conditions, what are some key factors, some identifying marks that maybe would tell us before we did all of this work that maybe the ratio test is not going to work. And so similar to kind of chapter 7 where we had a strategies of integration section, 7.5, that's essentially what 11.7 is. And so next time we're going to talk about maybe how could we tell that this is going to happen to us before we go down this path. Of course, we're here in the ratio test section, and so we have to try it though, right? All right, so with this, let's go ahead and move on, right? The ratio test did not work. How would we figure it out, right? Again, our task is not to just apply the ratio test. Our task is to figure out, does it absolutely converge? Does it conditionally converge? Does it diverge? What's going on here? And so the first bit is that I'm going to try to test, does it absolutely converge? So I'm going to look at summing up the absolute value of our series here. So -1 to the n minus 1, n over n squared plus 3. Apply those absolute values. And of course, those absolute values, as we saw before, those really influence that alternating piece. So the alternating piece, the -1 raised to some power. So that's just going to become 1. And we have n divided by n squared plus 3. And I guess, right, we could not even write the 1 if we don't want. That's fine. Just move that over. And now we have to decide, does this converge or diverge? And I'm going to go a little bit faster here, right? I'm just going to tell you the answer. I'm not going to show you every single step here. But the answer is you should use the limit comparison test with, and if you were to go through and kind of only keep the most important bits, well, on the top, there's only one bit, there's only the n, right? So you leave that. And on the bottom, the most important thing, right, as n goes to infinity, well, 3 is going to be nothing in comparison to, 100 squared, 1,000,000 squared, 1,000,000,000 squared, right? As n goes to infinity, that's going to be so much more significant. And so we're going to go ahead and compare with n divided by n squared, or that's going to be the same thing as 1 divided by n. Of course, that diverges by p series. So if you use the limit comparison test, compare against this, you can indeed show that this diverges, that these things share the same fate. And so this will diverge. And so sadly, it is not absolutely convergent, right? We were checking if we apply that absolute value, does it converge, right? That's what it means for absolutely convergent. The answer was sadly no. Okay, well, how about the original series, right? So if I just keep this -1 raised to the n minus 1, n divided by n squared plus 3. The claim is we can actually use the alternating series test, right? After all, it is an alternating series to show that this will converge. So when it's not absolutely convergent and yet the original series does converge, that's what it means to be conditionally convergent. So the series converges conditionally. All right, so that is my final answer. This is a conditionally convergent series. All right, how about we try another one? This is kind of a similar flavor here. Please go ahead, pause the video, take 2 minutes, 3 minutes, 5 minutes, however long it takes you. Try this one on your own. Pretend that this is your quiz or exam problem. Get as far as you can, and then come back and we'll spoil the surprise together. All right, so as I promised, this one was indeed similar to the last one. Here's yet another case where the ratio test is sadly inconclusive, that you do all this work and yet you get 1. So we go on and we try to think about, okay, well, how can we figure out if this is absolutely convergent, conditionally convergent, or divergent? And so if you apply that absolute value, and again, you try to think about, okay, how could I figure out if this converges or not? Remember, with those natural logs, they usually have some issues with the limit comparison test, but the direct comparison test, right, you can compare with a smaller function here, and the smaller one, when you add them all up, this series diverges because of p series. And since this diverges, well, certainly a bigger function, right? If this goes to infinity, there's no way that a bigger series doesn't also go to infinity. And so it will diverge. And so sadly, it is not absolutely convergent. And yet you can show using the alternating series test that indeed the original series converges, right? It's alternating, that this positive piece right here, the limit goes to 0, and that it's decreasing. And so that's what you need for the alternating series test. And so when you have the absolute value diverges, but the original series converges, that's exactly what we mean when we say conditionally convergent. All right, so that is it for this video. I hope you guys enjoyed. If you have any questions, please, again, post on Piazza. We'll try to respond as soon as possible. I will see you guys next time. 11.7 strategies for integration, right? When does the ratio test work and when doesn't it? That's what we're talking about next.